let's talk about the chain rule. For multivariable functions. We'll definitely get to problem 7 or something like it, but take it. We'll get there in a little bit. So let's look at a couple of examples. Oh, and I should look at all your symptom surveys too. I've been forgetting to do that. I'm supposed to be better about it. So please let me see your symptom surveys. Thank you. There you go. And thank you. Great. So let's look at a kind of real-ish example. There's so many things on this table here. So let's look at the following chemistry-related example. Cool. So the pressure, which we'll denote by capital P, in kilopascals, everyone's favorite unit of measurement, the volume, V, in liters, and the temperature in degrees Kelvin of 1 mole of an ideal gas are related by the ideal gas law, which you may or may not already be aware of. PV equals nRT, but in this case, the N times R is approximately 8.31. So there's our ideal gas law. Let's go with the following. If the temperature of a gas is 300 Kelvin and increasing at a rate of 0.1 kelvins per second, and the volume is 100 liters and increasing at 0.2 liters per second, how fast is the pressure changing? All right. So what we're going to do is we're going to write pressure as a function of the other variables. And then we're going to talk about how we use the chain rule to find the derivative here. So first of all, solving for pressure, we're going to write this as, color here, pressure equal to 8.31 times T times V to the -1. You can also write it as times T over V, but knowing I'm going to take derivatives in the very near future, I'm going to try and write it in the way that's kind of the easiest to differentiate. So here's what we have. We have the pressure as a function of both temperature and volume. We also, although it hasn't been written, it's certainly been implied that both temperature and volume are functions of time. Right? We are being told that the temperature is increasing at 0.1 Kelvin per second, meaning we could write a function for it if we really wanted to. We don't really want to. Similarly, volume is increasing at 0.2 liters per second. So volume is a function of time. This leads us to the idea of, and I don't know if he talked about this in class or not, but certainly when I'm talking about trying to find the derivative of a multivariable function where the function depends on some variables and each of those variables depend on some other variables, we like to draw this mapping because it helps us figure out how we're going to find the derivative of this function. So what we want to find is we want how pressure is changing as time is changing. In other words, we want dP dt. The nice thing about this is that if you've drawn this mapping, the way you get the derivative you're looking for is by finding all the paths that get you from the top thing to the bottom thing. Or in other words, from the variable that's the function variable to the independent variable that it's a function of. So when I look at this, I'm thinking, all right, I can either get from P to T by going through V, or I can get from P to T by going through temperature. So this first path, I'm going to have del P del V, that's how P depends on V. And then the second part of it is dV dt. This other path, I'm going to have del P del T, big T, del P del temperature, I should say, right? It's terrible when they use T for temperature and T for time, but it's pretty typical. And then from here to here, we're going to have dt, dt, d temperature, d time. So basically, it's all the paths to get from pressure to time added together. So the first path is del P del V times dV dt. Plus the second path is del P del T times dt dt. You might have noticed I'm saying del some of the time and d some of the time. The reason is intentional. I'm saying del when I'm talking about del P del V and del P del T because P is a function of two variables. And so when I take its partial derivatives, I should be saying del. But V and temperature are both functions of just the variable T. So when I talk about the derivative of V with respect to T, I'm saying dV dt. It's not a huge deal. Like, and if you accidentally write del instead of D, probably no one ever is going to care. But I'm trying to be precise because I'm trying to teach you the things. So I'm going to say it the right way. But definitely, if you have questions about it, don't hesitate to ask. So now we actually want to find how this is changing when the temperature is 300 kelvins and the volume is 100 liters. This is one notation for saying I want to find a derivative at a particular point. You could also write it as like P prime. I would probably not write it this way, but you could write it as P prime of 300 kelvins, comma 100 liters. To me, this doesn't feel great, but it's okay. All right, so I have to plug in the things. It's gonna be a little bit ugly. So I actually need to find the things, right? I didn't actually write down the things yet. So I actually still need to find what these are. So let's see. I have my function P equal to 8.31 times T times V to the -1. And I have that del P del V is 8.31 times T times -V to the -2nd. And I have that del P del T is just 8.31 times V to the -1st. It's not too terrible. And now I think I have all the functions I need to actually figure out what dP dt is at temperature equal to 300 kelvins, volume equal to 100 liters. It's going to be a little messy. And unfortunately, that's kind of often the case in this class is the numbers are often not very nice. Such as real life, right? A real biology applications calculus class, you're going to get some numbers that aren't that nice. But let's go ahead and see what we've got. So I'm going to have, maybe I still want this up actually. Let me put this back here for just a second. So I'm going to have my del P del V, which is this thing here. So it's going to be 8.31 times the temperature, which is 300 kelvins, times -100 liters to the -2nd, times dV dt, which we were told. We were told that the rate of change of volume is 0.2 liters per second. Plus, then I'm going to have my del P del T, which is 8.31 times volume to the -1 times dt dt, which is 0.1 kelvins per second. If I was trying to actually figure out what this was using a calculator, I'd probably do a little simplifying before I plugged it in. I would probably rewrite this as 8.31 times 300 times 0.2 over 100 squared, and then it's negative because there's a negative sign there, plus 8.31 times 0.1 over, just to make it a little easier to actually input into a calculator. Doing that work, we get that this is about equal to negative 0.04155. Now the question here, and it's an important question, is what are the units? Well, we're talking about how this is how pressure measured in kilopascals is changing as time, which is measured in seconds, is changing. How do I know it's measured in seconds? Because some of the other measurements were given in volume per second or temperature per second, right? My previous rates of change were 0.1 kelvins per second and 0.2 liters per second. So that's how I know what my unit of time is. Basically, it's just whatever unit of time they're already using. So this is going to be negative 0.4155 kilopascals per second. Fun. Great number, right? So easy to kind of get a grasp on there. I say sarcastically, it's not at all a great number, it's a terrible number. But the main idea I think I want you to see from this is the idea of drawing this diagram, where if you're trying to find the derivative of some function with respect to some variable, and there's some intermediate functions along the way, we want to draw this top-down diagram where you've got kind of like the outermost thing and the inner things and the inner things, and it can go on and on. Let's look at some more examples of this. Some more straightforward, less application examples, like the following. Suppose we had that our function f of xy was equal to x squared times e to the 4y. And we know that both x and y are functions of time. X is equal to sine of t, y is equal to cosine of t. And our goal is to find the derivative of f with respect to t. And sometimes, depending on the information we're given, there are multiple ways we can do this. In this particular case, we could find df dt simply by substituting in what x and y are equal to. So one way of doing this, the way we're not usually going to do it, but to kind of see that it actually does work, is we're just going to plug in x equal to sine, y equal to cosine. And so our function, f of xy, welcome, becomes the function f of t, and it's going to be x squared, so that's going to be sine squared of t times e to the 4 cosine of t. When you have a moment, I would love to see your symptom survey, please. Well, great. That's a function of t. We definitely know how to take the derivative of functions of t. So taking the derivative here, I have to use the product rule. Okay, it's going to be x. So the derivative of sine squared is going to be 2 times sine of t times the derivative of sine times e to the 4 cosine of t, plus, now we leave the sine squared alone, and we multiply by the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So e to the 4 cosine of t times negative 4 sine of t. And just to be super clear about what's happening here, right? If this is my f and this is my g, there's my f prime, there's my g, there's my f, there's my g prime. Cool. Now, that's not the way we're usually going to do it. Mostly because it's kind of tedious, right? Plugging in the function to another function usually makes doing the chain rule kind of not great. Alternatively, improvedly, I would say, we're going to draw this little diagram. F depends on what two variables? X and Y. And Y and X each are functions of T. So then we can see that df dt, well, again, I'm just taking all the paths that get me from F to T. And I should be more specific. When I go from F to X, the way I get there is by taking the derivative of F with respect to X. So to get from here to here, I'm going to do del F del X times from here to here, I'm going to do dx dt plus every other path that gets me from F to T. So then I have to go del F del Y times dy dt. All right, so let's find the things now. So looking at my original expression, del F del X, that's going to be 2x times e to the 4y. Dx dt, the derivative of x with respect to t, is going to be cosine of t. Plus, now doing this part, del F del Y, the derivative of this with respect to y is going to be x squared times e to the 4y times 4. And then dy dt, the derivative of cosine of t, is negative sine of t. Ooh, all right then. I should point out that this and this are the same. They look a little different because this one has cosine plugged in for every y and sine plugged in for every t. But if we went to this part here and we plugged in x equal to sine and y equal to cosine, these would exactly look the same as each other. But we don't do that unless we're asked to, really. There's no reason to do it unless someone says, do the thing. Questions about this one? So most of what I'm doing, I feel like the part that's new here is the drawing this diagram thing and then making sure we see all the paths. After that, we're still just using our regular partial derivative rules that we've already kind of seen. Yeah, let's look at a couple more examples and then we can look at, you said problem 7?
7.
Okay, 7. Okay, 7 looks interesting. I'm not sure about 7. We'll have to explore it together. So let's look at this next one. What time is it? Oh yeah, we got time. I want to make sure I actually get to the things you've asked about. So let's say we have this function of 3 variables. W of x, y, z is e to x times e to the y over z. And we're also given the x, y, and z are functions of t. Once again, we're going to be asked to find dw dt. All right, so I don't want to do it the quote unquote long way. I don't want to plug in t squared for x and 1 minus t for y and 1 plus t cubed for z and then take the derivative. We totally could. It would work just fine. It's not the point. Instead, we're going to do this thing where we say w depends on x, y, and z, and then x, y, and z all depend on t. So now my derivative of w with respect to t is going to consist of 3 things added together. There are 3 paths that get me from w to t. They're the path that takes me through x, plus the path that takes me through y, plus the path that takes me through z. Something I've noticed that you also might notice when you do this is that when you write this out, nothing cancels. But if you were to think of these derivatives as fractions, technically they're not fractions, but they almost act like fractions in every way that's kind of you would ever need them to. But if these were fractions, what could I cancel here in this first one? And dw, or I should say del w. If I pretend that the del and the d are the same, okay. What could I cancel here? The dx. What could I cancel here? And here? And the point is that the thing that's going to be left, if you could cancel those, is dw, or is del w del t, del w del t, del w del t. So the things that cancel leave behind the thing you're trying to find. It's exactly like the chain rule for regular functions. If you're trying to do this thing where you know that you have like y equal to f of g of x, and you're trying to find y prime, it's del f del g, or df dg, I should say, times dg dx. Derivative of the outer function, leave the inside alone, multiply by the derivative of the inside function. And again, you could think of the dg's canceling and getting df dx. All right, so then it's just calculation city. Del w del x is going to be e to the y over z. Dx dt is going to be 2t. Del w del y is going to be x times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, what's the derivative of y over z with respect to y? It's 1 over z, right? We have 1 over z times y. The derivative of 1 over z times y is just 1 over z. We have to multiply by dy dt, which is -1. And thirdly, we have del w del z. Okay, del w del z and del w del y are very similar. We're both taking the derivative of a constant x times e to the stuff. So I'm still going to get x. The derivative of e to the stuff is e to the stuff. But now the thing I'm multiplying by is the derivative of y over z with respect to z. So I might think of y over z as y times z to the negative first. So then when I differentiate it with respect to z, I get y times negative z to the negative second, or probably negative yz to the negative second. That's probably the easiest way for me to think about it. And then dz dt is going to be 3t squared. Kind of gross. These problems are often kind of gross. It's just the way it is. I wouldn't plug in what t was for each of the functions, but you could. So this is how I would probably choose to leave it. But one could, if they wanted to, or if they were asked to, is really more the situation. You could say that dw dt is e to the, okay, it's going to be kind of gross here, 1 minus t over t cubed times 2t plus t squared times e to the 1 minus t over t cubed times 1 over 1 plus t cubed times -1 plus, I'm not going to be able to fit it in here, x is t squared times e to the 1 minus t over t cubed times -1 minus t times 1 plus t cubed to the negative second times 3t squared. There's no good reason to do that, but someone might ask you to do something. So that's how you could do it if you really had to. We don't normally have to, so I would say ignore this for the most part, right? Sometimes you might need to find the derivative as a function of just t and not the intermediate variables. Usually not the case. Okay. So let's look at one more example like this, and then we'll address these two questions. Oh yeah, actually I have a question like number 11, so we'll do that for sure. So sometimes things are a little more complicated. Let's say that we have z equal to the inverse tangent of x plus 2y, and we have the x is equal to s squared times t, and y is equal to s times natural log of t. And just like every other time, well, not just like every other time, actually, a little bit differently here, we want to find the derivatives of z with respect to the variables at the base level, meaning the bottommost variables. We can write z as functions of x and y. And this one's gonna be a little bit different because x is both a function of s and t, and y is both a function of s and t. So I could, I'm not going to, but I could write z as a function of s and t, right? Z is some function of s and t. Okay, fine. I said I wasn't going to do it, but I'm totally going to do it. It would be the inverse tangent of x, which is s squared t plus 2 times y, which is 2 times s times natural log of t. So we could write z as a function of s and t. I want to find both del z, del s, and del z, del t. And then we're going to do it the usual pathway, which is to find del z, del s, which you could write as zs if you prefer. It's just going to be all the paths from z to s. So del z, del x times del x, del s plus del z, del y times del y, del s. It gets to be a little repetitive, right? But it's always the same thing. You're finding the paths from one thing to the other thing. And then we find what they are. So, okay, what's the derivative inverse tangent? I know it's probably been a little while. Just a quick reminder. The derivative of the inverse tangent of x is 1 over x squared plus 1. So the derivative of the inverse tangent of some stuff is 1 over your stuff squared plus 1 times the derivative of your stuff. I think that's the only inverse trig function derivative you really need to be aware of. I don't think you need to know the derivative arc sine or arc secant. Arc tangent's really the only one I think that it comes up in 17b and 17c. If the Dr. Liddell does mention the other inverse trig functions, let me know. We can definitely talk about them. But for now, I'd say this is just something you want to memorize. So the derivative of the inverse tangent of some stuff is going to be 1 over the stuff squared plus 1 times the derivative of that stuff. But the derivative of x plus 2y is just 1 because it's the derivative with respect to x. Times del x del s. X is equal to s squared t. So del x del s is going to be 2st. Plus del z del y is going to be, again, 1 over our stuff squared plus 1 times the derivative of the stuff. Now the derivative of the stuff with respect to y is going to be 2 because we're differentiating with respect to y instead of with respect to x. And then we need to multiply it by del y del s. The derivative of s times natural log of t is just natural log of t. I should really say the derivative of s times natural log of t with respect to s is just 1 times natural log of t because we're treating the natural log of t like a constant. So there's our not very nice looking derivative. I think you all should do the next one. So I want you all to find del z del t, which I will start writing out. So you guys should, I'll give you one. You work on it. I will point out you can definitely use part of the first one to help you with the second one. Those are the paths we're taking from z to t, the path through x and the path through y. I'm laughing because the problem I said I had that was like problem 11 is actually problem 11. Just fine. So the thing I was saying here is that del z del x didn't change, right? It's still the same as it was when we did it before. So we definitely know that the first part here is still going to be 1 over x plus 2y squared plus 1 times 1 if you really want, right? You don't really need to write the times 1. And then del x del t is going to be s squared. Sorry, can't quite see all the things. And then del z del y is going to be the same as it was before. 1 over x plus 2y squared plus 1 times 2. And then the partial of y with respect to t is going to be s times 1 over t. Or s over t if you like. And that's it. That's your partial derivative of z with respect to t. You might have noticed, you might not have noticed, here when I was talking about del x del t and del y del t and del x del s and del y del s, I was saying del because they are partial derivatives, because x and y are both functions of multiple variables. So when we differentiate them, we're doing partial derivatives. Again, not a huge deal, but just want to point out what's going on. All right, let's look at something like problem 11 first, and then we'll come back and we'll all see what problem 7 is all about. So here's problem 11. We have the following setup. If z is equal to f of xy, where f is differentiable, and we're given a lot of information. We're given that x is equal to g of t. We're given that y is equal to h of t. We are given that g of 3 equals 2, g prime of 3 equals 5, and the partial derivative of f with respect to x evaluated at the point 2, 7 is equal to 6. Similarly, we're given h of 3 equal to 7, h prime of 3 equal to -4, and the partial derivative of f with respect to y at the point 2, 7 equal to -8. All right. So they're asking us to find dz dt when t is equal to 3. And I will admit, it's always been a little confusing to me when they give you z equal to some function. Like, why didn't they just say z of xy? To me, that feels weird that they didn't just say z of xy or z as a function of xy, but it's fine. So when I make my little table here, or I should say my pathway chart, I'm going to start at the top with z equal to f, or really just f. I don't really need the z at all, although it's nice to have. So then f depends on x and y, and x and y both depend on t. We know this from these things here. We know that f depends on x and y, or z depends on x and y, either way you want to say it. And we know that x depends on t, y depends on t. Or using more formal words, z is a function of x and y are both functions of t. All right, I want to find dz dt. Well, we know how to do this. Do it over here. dz dt, I'm just going to take all the paths. It's going to be this derivative times this derivative. So it's going to be, and I do want to write del f because f is how they've written things down here. So that's going to be more useful to me. So I'm going to say dz dt is del f del x times dx dt plus del f del y times dy dt. Questions about that? Right, it's kind of the same as it ever was, at least as far as today is concerned. Now, it is worth pointing out that x is g of t and y is h of t. So that when I write dx dt, I could also write g prime of t. So I'm going to rewrite this as fx times g prime of t plus fy times h prime of t. It's the same thing, just using the other names I have for things. All right, so now here's what we want to do. We want to evaluate this when t is equal to 3. Okay, well, if t is equal to 3, that means x is equal to g of 3, because x is g of t, and g of 3 is 2, and y is equal to h of 3, which is 7. Not that, I don't know, I feel like it's important to say this. It might not be that important to say it. I kind of feel like it's important. So the reason I'm saying that is because then I know that when I'm finding f, the derivative of f with respect to x, I'm plugging in x equal to 2 and y equal to 7. So I'm really doing fx at 2 comma 7 times g prime of 3 plus fy again at 2 comma 7 times h prime of 3. And then we have all the pieces. That's going to be, let's see, fx at 2, 7 is 6. G prime of 3 is 5. Plus fy at 2 comma 7 is negative 8. Times h prime of 3 is negative 4. This ends up being 30 plus 32, which is 62. It's really a lot of bookkeeping, right? It's a lot of keeping track of what's what, but that's kind of it. It's really, it's not, I mean, it's terrible, don't get me wrong, but it's not so terrible computationally. It's just like we have to keep track of what everything is. And sometimes we want to say something is dx dt, and sometimes we want to say that same thing is g prime of t, or dy dt, or h prime of t, right? Those are the same, we just, the way it's written calls for one versus the other.